Oh. Okay, so let's start with the calculus limit. I wrote them down so that I could actually get something that worked. Make sure I wrote this down correctly. Oh, this is a square. Okay. I want the same rational function. Okay, first off, did I just ask you the same question 3 times? If we're not careful, we might look at it that way. No, I gave you the same quantity. I gave you the same rational function 3 times, but I asked for different limits. So going back to day 1, and by the way, I start limits literally an hour into the first class in Calc 1. When we're talking about limits, what are we asking? Are we asking for a functional value? I mean, look at the middle one. How do you evaluate at infinity? No, we're not talking about functional value. We're saying what happens as I get arbitrarily close to something. What is happening to the y value? So I'm going to go use the simplest one that we all remember, okay? I want the limit as x approaches 1 of x squared minus 1 over x minus 1. Now, if I were to draw the graph of that one, this is x plus 1 times x minus 1. Oh, this is going to look just like the graph of x plus 1, isn't it? Which looks like this. Now we got to go back to baby algebra for a moment. Question?
No, sorry.
Okay, so back in baby algebra, I mean literally remedial algebra, this is a problem that everybody did. And the reason you did this in remedial algebra is because you're going to use it so often in calculus. First question is, what is the domain of this? In words. What would you say?
The domain is negative infinity to positive infinity with the exception of x equals 1.
Okay, you like that? Can someone say exactly the same thing, but less mathy? Remember, you're talking to somebody in Algebra 1 now. You're absolutely correct. But that Algebra 1 student might, I think you might have just blown them away. What do you say? Too vague. Tell me what it, use the same, but use words instead of negative infinities. How about all reals except 1? You guys like that? By the way, you're saying the same thing. By the way, if I don't say all reals, is all reals the default automatically? Maybe, maybe not. You're in discrete math. In other words, we never use the real number line. We use different. We use rational or we use integers. Oh, yeah, I kind of need to say where it's coming from. Do we all agree that all reals except 1?
Yes.
In words. Yes, it's negative infinity to 1 union 1 to infinity open interval. That's absolutely correct. But I have to think way too much about that one. Okay? But algebraically, isn't this equal to x plus 1 after I cancel?
Yeah.
So you're in a remedial algebra class and you wrote this. Was that all you wrote? No, because the one on the left, the domain is all reals except 1. The one on the right gives the illusion that it's all reals. A domain cannot change except for the worst. If I differentiate something that has an endpoint, I lose the endpoint. But that's pretty much it. The domain can't grow. So what we did in baby algebra is, I call it the disclaimer. We throw that in there. These are equal. They are identically equal for every real number except 1. And by the way, I taught remedial algebra. You had to put this in there because otherwise the statement is not true. So when I'm doing this as a limit, can I say this? This, yes. This is a reminder of what you actually are doing with limits.
Yeah.
This says, I'm taking as x gets closer to 1. Does x ever actually equal 1?
No.
No. And by the way, some of you have a horrific habit that I cannot imagine you got through Calc 1 with. You use an arrow as an equal sign. An arrow mathematically is the same as putting a not equal. 3 plus 4 does not approach 7, because that would mean 3 plus 4 does not equal 7. Approach means you're closing in on it, but you never get there. You can't use an arrow when you mean equals. It is extreme other end of the spectrum. Yeah, and there are people that use, well, that's what I've always done. That's kind of like saying, and this is the way I make my 3's. No, I don't get to redefine what a universal symbol means. In fact, it's the single most important symbol used in the 3 semesters of calculus, more than the integral, because I don't get to the integral if I don't know what a limit is. Yikes. This means these are identically equal for all values except perhaps that one, because I never actually get to 1. That's why we can put an equal. So the first rule of limits is algebraically speaking. So this is what I always said in Calc 1. Cover the word limit. If algebraically this is equal to this, always except perhaps for that number, then the limit must be equal to the limit. That's the easiest way to say, did I do it correctly? Because we do a lot of algebra in limits, don't we? We do a lot of reduction and combining things. Now, as x gets closer to 1, x plus 1 is getting closer to 2. Does it ever actually get there? No, but the limit. There's a point right here, 1 comma 2, it has been removed. What do we call that? A removable discontinuity. Yeah, those are our favorite ones because they're the easiest ones to understand and see. This is identically equal to this for all real numbers except perhaps 1, and as x approaches 1, what is my function approaching? Think of a limit as if I could actually get there, where would I be? I can't actually get there because there's a hole there, but if I could get there, where would I be getting to? The number 2. That's why the limit is 2. Limits don't approach. Functions approach, limits equal. Limit is, where would I be if I could get there? Where is the hole? So this is what we did. Hopefully you did this on the first day of Calc 1 to kind of give you the idea. Now, what if there is no hole? Then is the limit going to equal the functional value? It's not a trick question. I mean, if I just have a nice pretty graph, I have a parabola, I have something. Well, if there's no discontinuities, then the limit will equal the functional value. But it's calculus. There's always discontinuities. They're more interesting anyway. Now, what if I let x grow without bound? You know, you did this one, but only a little bit later. As x grows without bound, what's happening to y? Is it also growing without bound? That's the way we say it. Without bound, unbounded means it's getting either bigger positively or bigger negatively, but it's without bound. It doesn't equal. So my y values are getting bigger and bigger and they're unbounded, so the limit is infinite. There's no functional value of infinity. You can't evaluate infinity. Infinity can only be reached by a limit. It's not possible to calculate infinity. Infinity is the result of a limit. But man, it's a common answer, isn't it? And it's one that hopefully is fairly simple. So these two problems that I just asked are quite different. One, I had the removable discontinuity and I did it. The other one, something completely different. I just gave you the same function twice, but the way I do these is going to be very different. Now, I'm going to spend just a moment reviewing the single most important thing you learned before calculus. Well, it's not one thing. It's like, in a good pre-calculus class, it was probably a month. It's called the fundamental theorem. Fundamental theorem of algebra. Can't get to calculus if I don't know this one. This is the one you have many different names along the way. Oh, I remember doing that stuff. Simplest. I'm going to give you an nth degree polynomial. It looks like this. Put some dots here. This is the n here just to remind me that it's nth degree. I don't need the n there. The thing on the right is a polynomial, so tell me about my exponents. If it's a polynomial, tell me about my exponents. Yeah. They are 3/2, -4,
Integer.
2/3. They're positive integers. They're all my exponents. That's not a polynomial unless all my exponents are positive integers. This is just a constant now, isn't it? Now, assuming that the a's are real, why wouldn't they be? actually there are no rules that say any part of this has to be real. Assuming the a's are real, I absolutely know this is equal to a n. I'm going to factor that out. X minus R1, X minus R2, X minus Rn. Okay? This is an absolute, no exception. Every nth degree polynomial has exactly n factors. The r's are called the roots or the zero of the polynomial. So think of something like a simple quadratic, x minus 3 times x plus 5. Then I can easily identify my r's. I factored out the lead coefficients, so all these coefficients would have 1s on them. Now, this is every polynomial that exists. This can be done. Now, the r's. R's are real numbers, or can they be complex? Ooh, what if one of my factors was, x squared plus 4? What if that was one of my factors? No, I'm saying you can write it in this form. Well, then that would be x plus 2i times x minus 2i, and I would have two imaginary roots. Oh, so the irreducible quadratics, we've used that term recently, have complex roots, don't they? So this is what you remember. By the way, you saw a little bit of this in elementary, a little bit in intermediate, and hopefully a lot of it in pre-calc. These r's can be repeated, and they can be complex. And if they're complex, they generally always come with what? Complex roots generally come in what? 3, 7, 5? Every time you've ever had a complex number in your entire life, without exception, it always came as what? Pairs, complex conjugates. You've never in your life dealt with a single complex number by itself as a result. They came in conjugate pairs. Is that a rule? Only if the coefficients are real. If the coefficients are allowed to be complex, then the complex numbers actually don't come in pairs. That's kind of crazy. But if my coefficients are real, the complex numbers come in conjugate pairs. Oh, okay. So I have exactly r roots. Some may be repeated, some may be complex. Okay, but this is every problem that exists. So now going back to baby algebra, going back to this thing, if P of C equals 0, and you did this, remember your rational root theorems in pre-calculus? You looked at all the coefficients of this guy, all the factors of this guy and all the factors of this guy, and you considered every quotient. Remember you wanted to whittle it down into something smaller and smaller and smaller? I started 4th degree, you found a root, now you got a 3rd degree, synthetic division. Then you got down to 2nd degree, quadratic formula. You guys remember doing that? Of everything you did in pre-calculus, that's actually A number 1. That's the absolutely most important thing you do in all of pre-calculus is that. That's part of the fundamental theorem of algebra. But there's a piece that you learned in remedial algebra. It's right here. If P of C equals 0, then x minus c is a factor. That's an absolute rule. In fact, what would I do next? I'd say, let me take this and divide it by x minus c using my synthetic division so I can now whittle it down to a polynomial of degree 1 less. Hopefully that rings kind of a bell. Okay? And I do stuff like that. So if I can do that, so going back to here, if I can evaluate this at 2, do I have to do a lot of algebra? If I can evaluate that at 2? No, I don't have to do anything. I can just evaluate it. Why? Because it means nothing weird's happening. So the very first thing we are doing is, let's evaluate this at 2. It says 8 minus 4, that's 0. Oh. This would be 8 plus, what? 8. 8 plus 8, sorry, minus 8, but that's also 0. So we say this approached the form. Please do not tell me this equals 0 over 0 for 2 reasons. 0 over 0 is not a number. It's a form. It's called an indeterminate form. And the moment I put in equal after the limit, then that means that is my final answer, no matter what. If I write limit equals and I put something numerical, none of you would say the answer is 4 and that equals 7. Well, okay, I would hope none of you would say that. If you're telling me the limit equals a number and then later tell me it equals a different number, that's a problem, isn't it? No, it's not a number. It's a form. Why is that important? Because what is the form this one takes on, by the way? This one, we say, takes on the form of infinity over infinity, which is a different indeterminate form. By the way, if you didn't learn this in your Calc 1, then somebody did you a great disservice, okay? Because they're telling you that you're just randomly putting down stuff on a piece of paper when you're calculating limits. No. If I can't evaluate my limit directly, I have to figure out the form, because the form tells me the strategy. The strategy for the first one is completely unrelated and different from the strategy of the second, even though they're both indeterminate forms. The strategy of the first one is a factor and cancel. How do I know I can factor and cancel? How do I know that? I know without any doubt. I absolutely know this without any doubt. How could I possibly know that? Because I just evaluated the numerator at the number 2 and I got 0. That absolutely means that x minus 2 is a factor. That's fundamental theorem of algebra. You know that. That's not something you have to prove. You know that. The denominator, I evaluated at 2 and I got 0. That means x minus 2 is a factor of the denominator also. I like this kind. It's a factor and cancel. I just don't know how to factor that cubic in my head. This is why you learn synthetic division. This is the only reason you learn synthetic division, because this is the problem that synthetic division is designed for. There's a lot of uses for it, but it's basically this, that I want to whittle a polynomial down. So let's do the numerator first. So what is my root? Careful, what's my root?
Should be 2.
Is it 2 or is it negative 2?
2.
So it's x minus root. It's the number 2 that made the quantity 0, not the number negative 2. So I always remind folks that, because do we sometimes put the opposite sign there? Yeah, in a lower level algebra, that's probably the number 1 error. So now let me put all my coefficients in descending order. What are they?
0.
0. My coefficients in descending order?
1.
How about 1? You can't start with a 0. Then what? Then,
Negative 2.
am I done? Because there's no constant term. I do need the placeholder. That 0 is important. That can't be a 0 because I can't start with 0 of something. Now, remember, bring it down and now multiply, add. 2, add them. 2, add them. 0, add them. What does that mean? That means I have 0 remainder. That's a good thing. Agreed? So, what does this mean for my numerator then? It factors as what?
X squared plus x.
So it's remainder, constant, linear, quadratic. So it's x squared plus
Negative.
remainder, constant, linear, quadratic. Those are coefficients of my, so how do I read it?
X squared plus x.
X squared plus x. If I'm not sure, can I just multiply that out to do a quick check?
Yeah.
Might that be wise in general? It's not very hard. Yeah, because could I have made an arithmetic mistake along the way? Or worse, the wrong sign? Yeah, it can happen. All right, now let's do the bottom. What's funny is this is a huge portion of probably the first 3 weeks of Calc 1 that a lot of people say, oh, we kind of rushed through it. And it would be unfortunate if you did, because we use this all 3 semesters. In fact, you use this even in DiffyQ, because not always in the same capacity, but it all is interconnected. So my coefficients for the denominator would be what?
1, 2, negative 4, negative 8.
And when I bring those down, and then 2, add them up, 8, add them up, 8, add them up. That's important. If that's not a 0, then it means that x minus 2 was not a factor. But it had to be because we did the first thing. So if that's not a 0, it means I have an arithmetic error here. Now, how do I read that one?
X cubed squared.
Plus 4x plus 4. Now here's the big deal. True or false? Original problem equals this new problem. True or false? You have to have certainty. There's no gray area here. There's absolutely true or it's absolutely false.
That's true.
What did we just do? We factored and canceled the x minus 2. My favorite terminology, because most of you were in Calc 1 with me, I always call that's the problem child, isn't it? X minus 2 is the problem child. X minus 2 is the reason I was getting zeros on the top and bottom. And I have just removed the problem child from the problem, meaning x equal 2 is a removable discontinuity. So we're saying algebraically that this quantity here is identically equal to this quantity for all real numbers except perhaps 2. But I don't care because I'm never going to equal 2. I'm only going to approach 2. Now, by the way, it matters not what the numerator is doing. You know this. It really only matters that the denominator. If my denominator was approaching 10 and my numerator was approaching 0, is that a problem? No, that would be 0. If my numerator was approaching 10 and my denominator was approaching 0, would that be a problem? Yeah, that's a huge one. And if they're both approaching 0, then it's fun, because that means I'm going to factor and cancel. You don't like the denominator only. That one, that's the last one, by the way. Okay, so can I try to evaluate this one then? Whatever the graph of this is, there is a hole where x is 2. But what is the y value where that hole is? That's what we're about to figure out. What's my numerator? 6. And my denominator? 4 plus 4. Did I do that right? 4 plus 4.
4 plus 8 plus 4.
Or 4 plus 8 plus 4, sorry.
16.
I can reduce that, I'll reduce it. If you want to know what does this actually mean, it means whatever the graph of the original problem was, there is a hole at 2 comma 3/8. So the limit as x approaches 2 is the y value of 3/8. Beautiful. We did a factor and cancel. It was a lot of work. I don't really want to do this in general if the degree is high, but I always can. Every rational function, you can always evaluate a limit no matter what it is, because you can always do the algebra. Now, the middle one. That's the most interesting one of the bunch, because that's the one we're going to actually use the most today. The middle one, the very fact that it factors is really not relevant. It's, by the way, could I take the middle one and then do this one and say it equals this? Could I do that? I could, but there's really no advantage. Let's say the middle one is the only question you're being asked. There's no reason to factor it at all. It's x is approaching infinity. I had to factor it because x was approaching 2 and that gives me a 0. But now I'm approaching infinity. So, lest we forget, okay, I want to remind you of something because it's a simple algebraic step, but sometimes we forget the obvious things. Let's suppose I have the following polynomial. I have x to the 4 minus 3x cubed plus 2x squared over, I don't know, 4x cubed minus 5x squared. Okay. I want to simplify this if possible. You see x is all over the place. So what do most of us do here? Hopefully.
Long division.
Get rid of the x.
I could do long division, but I'd rather get rid of the x's. If I'm going to do long division, maybe. But first, how about we get rid of the x's? Do you agree with that one? Because I may be taking a limit at some point. So we'd all do this, hopefully. We do probably something like this. Can I cancel those x squareds now?
Yeah.
Yeah. And by the way, if you wanted to do the long division, that would have been correct, but this might be easier now because the denominator is linear. Would we agree that that's probably something we'd want to do? Everything I said there is true and correct, but that's too much work. That took 2 steps. I don't want to do 2 steps. I told you guys this before. Almost every algebraic process you've ever learned in your life can actually be done in 1 step, regardless of what the question was. There is no such thing as reducing a quotient that should require more than 1 step. How can I do this in 1 step?
Multiply the top and the bottom by 1 over x squared.
Perfect answer. That's 100 miles easily. It was an easy answer, but you remembered. And then the next thing I have will be the final answer, won't it? This is the trick. Well, I don't like this. This is the technique we're going to use. Don't factor. Well, first of all, it might not factor. The thing here, see, it doesn't actually factor in terms of the x's. But this process here, now, going back to here, do we all agree that numerator and denominator grow without bound? They're both going to infinity, which makes a problem. Infinity divided by infinity, obviously that equals 1, because I just cancel infinities. No, and you guys remember there was a trick when you looked at degrees, right? If the degree on top was bigger, it tended towards infinity. If the degree on top was smaller, it tended towards 0. If they were the same, I got a constant. You guys remember those rules, right? But why did those work? Because you did that. And that's actually what you're going to do most of the time, because you're not always going to be dealing with polynomials. You might be dealing with something else that can't be done that way. I might not have degrees. So where am I looking? You're always looking at the denominator. Now, I'll just make a simple assumption that numerator and denominator were both written in descending order. Not because that's a rule, but that's convenient. Right? None of you writes a polynomial and just randomly writes the terms, do you? Because it makes factoring kind of a nightmare. So both numerator and denominator have degree 3. But it's only the denominator. If the numerator was not degree 3, it's still the denominator's degree of 3 that I'm concerned with. So I'm going to multiply top and bottom by this. Does that change anything? No, you can never multiply or divide by something that could potentially equal 0. X is not 0. In fact, X is growing without bound. I think 0 is the least of my worries, right? I'm going as far from 0 as I can. So what do I have next? I now have 1 minus 1 over x minus 2 over x squared. And on the bottom I have 1 plus 2 over x minus 4 over x squared minus 8 over x cubed. Now I'm only going to do this one once because I don't like this next step. You know that the limit of a quotient, keep going, is quotient of the limits, and you know a limit of a sum is the sum of the limits. So technically, like I said, I only want to do this once. You see why I only want to do this once, because this takes so long. All right, absolutely this statement is true. Can I evaluate each of those limits independently? Yes. Lest you forget, the later ones we sometimes forget, but a major theorem that was actually proved using epsilon delta. In my class, this is the 4th lecture of the semester. This one's important. We prove that that limit is 0. Okay, that's actually a very, very important theorem. So what about if it's a higher exponent? Well, remember, I'll put a number. Let's say 4th power. Well, isn't that true? Oh, and that's still 0. So if it was a higher power, I don't need to rewrite it. I know. Why is this important? Because it means that I know that this limit is 0, this limit is 0, this limit is 0, this limit is 0, this limit is 0. What is the limit of a constant? Always the constant. By the way, it wouldn't matter what I'm approaching. It's the limit. Oh, there's a 1 there. The limit of 1 is 1. It never stops being 1. So after all of this, my answer is just 1 over 1. Now, I could have used the degree argument. Absolutely, you could have, but what if this was a square root? What if this was exponential? What if this was logarithmic? What if this was sine and cosine? Well, then that won't work. So what do we do, hopefully? Here's what I like to do. It's kind of shorthand. Isn't that true? Don't all of these terms approach 0? Meaning their limits are 0. By the way, does 1 over x ever equal 0?
No.
No, but it's closing in. It's getting, the bigger x gets, the smaller that quantity gets. It never equals 0, right? But it gets smaller and smaller and smaller and smaller. So this is what most of us probably did in Calc 1, right? We just goes to 0 easier. So the answer was 1. But the key was doing the top and bottom thing. Well, if this was a Calc 1 test question, I'm going to have one of two things. Either you did this and said the answer is 1, or you said it's 1 because the degree of the numerator equaled the degree of the denominator. And I like that answer. But it only applies to rational functions, remember. It doesn't apply unless these are both polynomials, which is not always going to be the case. In fact, for the rest of the class today, it will not be the case again. So that using the degree in your argument won't work if there's a square root or some other function. Now the last one, I'll rewrite the last one. Is this one. This is our least favorite. We hated this one. Remember, there are only 4 types of discontinuities. Removable is our favorite. Break. Remember the break in the graph? You hate it. Usually it's a piecewise function. I don't like that one.